Okay, we're ready to do the centripetal force problem of a banked roadway that has friction, mu. And so we're going to want to define an axis system. I defined x as positive to the left and y as positive up. And my question is, what provides the centripetal force? So I'm going to look at the sum of the forces in the x direction. And the only force in the x direction is the centripetal force. And as always, I ask the question, what provides the center-seeking or centripetal force? What does? Well, I have a normal force from acting from the roadway onto the car, and there would be an x and a y component to that. So the x component, positive in this direction, will equal the normal force times the sine of theta. And I also have the part of friction that's acting here down the plane. I have the piece of that acts in the x direction, positive this way, so that's going to be plus mu times the normal force times the cosine of theta. So that's the force in the x direction. It's only the centripetal force, and it's composed of two pieces, part of the normal force that acts in this direction, in the x direction, and the part of friction that acts in the x direction. What are the sum of the forces in the y direction? The car will start to slip when the y direction, up and down, is 0. That is the limiting case of slippage. And what are the sum of the forces in the y direction? Well, we have negative mg, because it's positive downward and we're counting up as positive. So it's minus mg. We have a piece from the normal force acting in the positive direction, and that is the normal force times the cosine of theta, and the part of friction that acts in the upward direction, which will be mu times the normal force times the sine of theta. So we've got quite a bunch of stuff to solve here, and I want to make sure I haven't made a sign error anywhere. So my mv squared over r is positive. My normal force in the x direction will act this way, which is positive, and my friction force will act this way, which is positive. All good there. In the y direction, we have mg acting downward positive. We have the normal force, which is a cosine piece, and it is positive upward, so it stays positive. And I also have this part, which is in the negative direction. It's acting downward. So it's always good to stop, make sure you've got your sign conventions right. I'm going to factor out n and get cosine of theta minus mu sine of theta. And I'm going to carry the mg across the equal sign, changing its SIGN sign to positive. And so the normal force is equal to mg over the cosine of theta minus mu sine of theta. And I can plug that directly in for the normal force here. And get the grand equation that V equals the square root of R, M, and the M's will cancel. So I'm going to get RG, and on top I'm going to have sine theta plus mu cosine theta, and on the bottom I'm going to have cosine theta minus mu sine theta. And that is my limiting case for the velocity when both a bank angle, theta, and friction are present. So first we started with a level surface that had friction, and then we had a banked curve with no friction, and now we brought them together. Does it make sense? Well, suppose theta is 0. When theta is 0, the sine of theta, the sine of 0, equals 0, and the cosine of 0 is 1. So when theta is 0, the velocity will be the square root of rg, and the sine of theta is 0, so these guys are 0, and I get mu cosine theta over cosine theta, which are both 1, so I get mu. That's the level surface with friction, no bank angle. And that's what we got when we did it a couple of videos ago. What happens if theta, if mu is 0? If mu is 0, both of these go away, and I get sine over cosine, which is tangent of theta, these guys, and I get rg tan theta square root as the limiting case. And that's what we got when we did the banked curve with no friction. So the limiting cases for this equation are correct. Now, I defy anybody to derive these equations separately in the directions of motion. If you use this axis system, where this is x prime, and y prime, I defy you to get out the other end. You can try it. If you're like I am, you like to prove the teacher wrong on all occasions that you can. When Mrs. Milliron told me in 3rd grade it was impossible to trisect an angle, I spent great amounts of time trying to prove her wrong. And I came up with a method that worked for 60, 30, 45, and 90 degree angles, but those are ones for which it is possible. So I won, and yet I lost, since it wasn't a general case. So when we have a banked curve with friction, this equation is the one that allows us to have both mu and theta present, so friction and a bank angle. And it's worth memorizing in case it comes up on the test, because you do not want to derive this. I mean, I almost made a mistake with the signs doing it on the fly. So, which is why teachers come in with prepared sheets of paper, because they hate making mistakes when they're lecturing, as do I. So that's why I went and checked it to make sure it looked right. So this is we started with a flat surface with friction, banked surface, no friction, banked surface with friction, all talking about centripetal or center-seeking forces that hold the car in orbit, so to speak.